conventional entry motor, you have an iron core here. But for this machine, we are replacing this iron core with a reinforced plastic fiber. And then we are going to have two phase coils. We call it phase coil A and phase coil B. And then we'll have the same thing on the rotor side. So this side here is what rotates. And we are going to use wireless power to induce current in this rotor side and then make the machine rotate. That is the fundamental concept of the machine. So, but to do that, we have to model, that is, we try to understand how that motion is created. So it's difficult to analyze a machine in its full form, that is in 3D form. So what we do is that we try to use like a plane to cut the machine on the XY, like on the XY plane. If you do that, you're going to have like a two-dimensional section of the machine. In this two-dimensional section now, you can analyze it and come with the full model of the machine. And this is the electric circuit of the machine. So this coil here is what you see here in blue, and then this coil in red is what you see here in red. So this is the stator side of the machine, and then this side is the rotor side of the machine. So this side basically is attached to this main part in the machine that is rotating. So this part rotating here is the coils that are inside here. So we first start by analytically modeling the magnetic field of the machine. So we try to understand when current passes through the coils in the machine, take a single phase coil, and then we come out with a general magnetic field that describes the whole field of the entire machine. This one is for a single coil, and then we try to extend it for the entire coil or for the entire portion of the machine. So if you calculate the magnetic field of the single coil, that's if you consider this single coil here, you can come out with this magnetic field. Then what happens if you have to calculate the entire magnetic field of all the coils around the machine? So this one is the final equation that describes that mathematically describes the magnetic field of the machine. And then if you use that mathematical equation now to try to plot the magnetic field of the machine, you have something like this. So you see that the equation actually works. The next stage was to now go further and develop the inductance of the machine. And for us to develop the inductance of the machine, we have to first look at the field flux. And then with the field flux now, we'll divide the field flux by the current, we can get the inductance. But the field flux is already calculated here. So what we do is we just divide this field flux by the current, and we have a model of the inductance. So this inductance here describes, this is the inductance of the coils that lies in the machine. So if you were to wire this machine, the inductance, you can calculate the inductance in 2D for the machine. So the next part is to try to calculate for the inductance has two parts. So the inductor has a part that is due to the external part of the external field in the coil, and then it has another part that is due to the internal current that passes through the coil. For the one that's the field that is external to the coil, you can easily calculate it. But for the one that is internal, it's not so trivial to calculate. So we have a general formula that we can calculate, but it's difficult to extend to get a general formulation. So what we do is that we can calculate it for different pole pairs of the machine. So to understand it, so what we do is we calculate for if one pole pair, 2, 3 pole pair, and then see if we can generalize it. But yet, it's still very complicated. So we leave it like that, and then now we try to analyze and see what happens. We take, let's say, an example model of the machine, and for the example model we take these are the parameters that we analyze analytically. Let's say we take a machine with the outer range of 100 millimeters, and when we do that, we calculate now the inductance of that machine if we were to use wires of 1 millimeters to wire it, 2 millimeters to wire it, 4 millimeters and 9 millimeters. Then we try to study how the internal inductance behave and how the external inductance behave. So when you do that, you realize that not all inductances are significant. So we can use the most significant inductance to describe the inductance of the machine, depending on the kind of wire that we use. So if we were to use for example, if we were to use very small wire for one pole pair, you realize that the internal inductance is very small, it's insignificant. So we can just calculate just the external, the inductance due to the external field, and just get the total inductance of the machine. So this kind of analysis permits us understand how we can easily calculate the inductance based on how the machine is wired. Then from there now we can get the general formula that describes the inductance of the stator coil and the inductance of the rotor coil. And we can then calculate the inductance analytically. The next stage is to calculate the mutual inductance. How does the inductance behave between when there is coupling between the stator and the rotor coils? So we still follow the same analysis, and we can then develop the mutual inductance of the machine as the machine rotates. And we try to plot that mutual inductance and see how the inductance is changed when the machine is in rotation. We also go further to calculate the coupling factor. Coupling factor means that we try to measure the strength in which the stator coil and rotor coil, how strong they are linked together. It's like a factor. When it is 1, it means that it's like totally connected together. And then the more it reduces, it means that they are not very strongly connected together. So you can come up with a formulation how to estimate that factor. And now the next part is to develop a frequency model. For the frequency model, we try to see how we do a detailed analysis of the electrical circuit of the machine. In the electrical circuit of the machine, we can come out with a full feel of how the machine is, the field flux between the coils. This field flux between the coils will come with this matrix, and from this matrix we can come out with the inductance of the windings of the inductance matrix of the machine. We go further now to analyze the electrical circuit of the machine, and if we do that, generally the machine looks like this. So the machine has 2 power sources. You have two power sources that are 90 degrees out of phase. So one power source is connected to one phase coil, and then the other power source is connected to the other phase coils. So I use the color red and blue to indicate the different phase coils, the different phases of the coils. If we can go further and then we do that, we are going to get all the voltages, the voltage expression of the voltages in the different coils. The next stage is now to develop analytically a torque model. So we want to describe analytically how the torque of this machine behaves and do further analysis. And if we do that, we can describe a torque model that is voltage control and current control for the machine. And then now we try to develop a resonance frequency model of the machine. So we want to develop to see how we can calculate the resonance frequency. But the most important aspect of this is to how to estimate the capacitors that we have to add to the coils during resonance, because the resonance frequency we choose it as the target frequency. So if we do more analysis of the circuit, then we have the resonance frequency in this model. But with this model of the resonance frequency, we realize that from the domain of definition, we can eliminate all frequencies that are in the negative domain, and then we can eliminate all the higher frequencies that are smaller because their effects are very small. So we just have the most significant part of the frequency, and it means that the frequency model is in this way. We have like frequency splitting at resonance. And then we can, with this formula, it means that if we calculate the inductances and we know the frequency, we can estimate the capacitor that we need to add to the coils. Then we try to come out with some sort of like a design methodology that you can follow if you want to use the analytical method that was developed. So for the design methodology, what you do is, the first thing is to decide, you have to sort of decide the size of the machine. That is the outer radius, the inner radius, the coil and all that. From that size that you decide, you can calculate the inductance of the machine. And if you calculate the inductance of the machine, you choose a target frequency. Then you can calculate with the resonance frequency, you can estimate the capacitance that is needed. Now you have the resonance frequency, you have the inductance calculated, and then you have the capacitance value. So what you need to do now is to study the torque characteristics of the machine. So you can then follow this procedure, mathematically following our model to understand the behavior of the machine. But this process that we have described mathematically, we need to validate it somehow. So we choose finite element analysis to validate the process. So what we do is, we are going to understand how to validate the finite element analysis, we have to use the model of the machine. Then for finite element analysis, what you do is, you first of all try to decide an analysis model that you want to use. and then you try to understand the physical phenomenon that happens in the machine when the machine is in operation. Then we try to connect that analysis model to the physical phenomenon. So we are going to use this model of the machine as an analysis model. Then for the physical phenomenon that happens in the machine is that we know that there's going to be resonance because of the inductance. So what we do is we try to create now an inductance model first. With that inductance model, we use the model of the machine and then determine the inductance of the machine through analysis, through finite element analysis. Then we decide the capacitance and then we run now magnetic resonance analysis still with the model of the machine. And then we can do torque analysis. All of this with finite element analysis. So the procedure is quite elaborate here. So the procedure will first create an inductance model. So in this research, we use JMAC analysis tool as the main finite element analysis tool. So what we do is that we take just single pole coil because we don't need the entire machine. We just need to calculate the inductance of the coil. So we can take a single pole, and then we use this model, we run this analysis and calculate the inductance of this coil. When we have this inductance now, we determine the capacitance value through a target frequency. When we have the capacitance value now, then we run now a magnetic field analysis. And then for the magnetic field analysis, we have the circuit is different. Then for the magnetic field analysis, now we can run a portion of the machine. And after running this magnetic field analysis, you can do some sort of optimization because from the magnetic field analysis, you can study how the machine behaves and you can change some parameters. After that stage now, then you run the torque analysis now to see when the machine is in motion. Then if we do that, we have the inductance model. For example, when we run the inductance model of this kind of machine, let's say we have these are the typical analysis conditions that we use during an inductance model, and this is how the solver, the JMAC solver, is going to determine the inductances, both the self and neutral inductance, and then from there now we can move on to calculate the resonance. But now, analytically, we have determined the resonance model that we can use to calculate the capacitance. But what you have to note here is if you look at this is a circuit used for the magnetic analysis inside the analysis model, and this is the one used analytically. What you realize is that they are actually similar. So it means that we are going to use the same frequency model to determine the frequency. So we use the same frequency model and determine the frequency, and then use that frequency for both analyzing the machine mathematically and then running it through finite element analysis. So the frequency model is still the same because both circuits are interlinked. And then now, at this stage now, we can now run now a magnetic field analysis now with the determining capacitance through the frequency. And if you do that, you will have something like this. If you run it now, you see that, for example, this is the main coil that is powered, and you see how the rotor coil is actually induced if it is properly done. And these are some typical values that we use during the simulation. Then now the final stage now. So to combine the entire process of the final element analysis to validate the mathematical model, this is what we do. We just first run an inductance model, run a magnetic field analysis model, run the complete magnetic field analysis model, and then now do the transient torque analysis model. So finally, in conclusion, the objective now has been attained. That's the objective is we first of all had a mathematical model that was developed through the research, and then now we validated the mathematical model now through the final element analysis. And a typical example is, for example, you see that let's take a machine that has 2 millimeters air gap, that is the rotor coils and the stator coils are separated in a distance of 2 millimeters. So if you are to calculate, let's say you take the radius of the wires that are used to wind the machine, it has, let's say, 9 for 2 millimeters. Then you are going to have, through the model, you have the inductance like this, and through final analysis, you have the inductance like this. And you see that the inductances are not so different. And then what you observe is, as the radius of the wire reduces, the models correlate more. So you see that we can use like our model we calculate the inductance, and then through finite analysis, we calculate the inductance. We can now compare and see, maybe modify and do some sort of optimization. Then, if an example is, let's say we use a 2-pole pair machine like this. We follow the same process, and the first stage is to, okay, the first stage is, you see that if for example, for this one, you realize that if it is properly run, you see, this is the machine now in motion, when all the stages that we described above is followed. And at the end of the day now, we have two top. We have the top that we can determine analytically for the same configuration of the machine, and then we have the one that is done through finite analysis, and we try to compare it. But we realize that, of course, they are almost, they fly within the same bandwidth, but the top response, however, of the finite analysis is higher than the one determined analytically. You still have to correct this. Now, the next stage of the research is multi-objective evaluation. So how do we evaluate and improve, let's say, a model of the machine that we are designing? We can do this through multi-objective evaluation. The thing that we can do is we first try to design the machine such that we calculate the efficiency of the power that is induced at the rotor side. So if we have to do that, we have to use like the quality factor and the coupling factor. For a typical, let's say, coupling factor of this, we can try to calculate the different inductances and then estimate the quality factor. The quality factor, however, when we calculate, is not, this is like different quality factors for this different machine. We need a quality factor that is very high, and this one is, we could get only like in tens of hundreds. And then now we can go further now to try to understand the efficiency. So we can work with, let's say, if we know that if the efficiency is high, it means that more power is induced at the rotor side. This can be some sort of way of optimizing the design. But in general, we have when we do the research, we always use JMAP to do optimization because JMAP gives that computing power. So what I always do is, first of all, on JMAP we can define some sort of objective function. So the objective function can be, let's say, the efficiency. We can use, let's say, the main constraints would be the inductance that we want to calculate, the like self-inductances, motor inductance, and the coupling factor. And then now the main objective function is to get the best resonance frequency and the best efficiency. So we'll design out different shape of this. We'll draw one of this model, and then the machine can calculate for different shapes and different sizes of wire for many shapes. And then let's say we'll leave it to run overnight to determine the best size of the machine and the best shape of the machine. And the process will be repeated inside the JMAP software many times, and we can get optimal design. So we use this kind of procedure to get the best design of the machine. Now, we extended the main study of the research. So of course when the stator and the rotor coil are radially placed, we developed the analytical model and we could verify it and validate it through finite analysis. So we extend the way in which we place the coils. So now we decide to place the coils axially, and then if we place the coil axially, when the coil is radially, we have this is how the machine looks like. And then for radial shape now, we came out with the 3D CAD model of this machine, and we went further to do a detailed analysis now through finite element analysis because it's already validated mathematically. So through finite analysis, we went through the same procedure again to understand how the characteristics of this kind of machine. And the main architecture of the machine is something like that. So the machine is going to have like, for the axial, we call this one the axial gap type, is going to have 4 coils. And the 4 coils are going to be placed axially, 2 on the stator and then 2 on the rotor. So you have like the stator side and the rotor side. Now we have developed an analytical model of our machine. We have validated it through finite element analysis, and then we have tried to design an optimal way of an optimization procedure that you can follow to optimize the design. We extended the study to include axial machine. Now the next part now is to go back to the main research, which is the radial gap type. We try to develop an experimental prototype to test it experimentally. For the experimental prototype, first thing is the shape of the machine is like this. So the machine has the machine has 4 coils, 2 on the stator and 2 on the rotor. So this is going to be the whole coil disposition. It's going to have a lot of coils, and then the shape of the machine itself, we are going to look for a way to place the coil on the stator, and then the final machine is going to look something like this. So if throughout the years we have tried to get the best possible design of this machine, more so because the coils that we want to use to wind the machine is kind of very thick, and it's not so easy to place the coils on the surface of the machine. So we realize that this is the coil that we are using. We call it wrist wire, and this coil, this one has 280 strands of 0.2 millimeters wire. So we have one wire of 0.2 millimeters, and then the mesh, this one has 280 of them. So it's the initial stator coil that we developed, we realize that it's really difficult to wind it around this coil. So we have to look for a way that we can easily wind it, and so we can put the coils in place. And throughout the years, while doing multiple printing and multiple testing, we realized that if we can create like some sort of like a stator holder that will hold the main coils on the stator, and then that stator holder now we can place it now inside the main stator. And for the stator holder, we realize that if we do something like with the plastic, the 3D printer plastic, if we use 1 millimeter of thickness, it becomes flexible, like you see here. So it's flexible. So we did different design, we realized this was flexible. So with this flexible design now, we designed the main stator holder, stator coil holder. So it will hold the stator coil in place, and then now we can now do whatever we want to do with the coil. So we realize that now. So what we do is that with that stator coil holder now, the idea is when we have put the coil on the stator holder now, we can then put it now inside the main stator coil, just like a core, and it is removable. So you can remove it, and then you can easily wire it, and then you put it back, just like that. So now the next stage now is now to wind it now. To wind it, you have to create first. We first need to design a simple winder. So with this winder, when you wind the coil, it creates the shape of the coil that has the same dimension like the machine itself. And the process of winding it too was not so easy. Now you see, we put the coils face by face in place. We attach it with some sort of plastic. When we have it stay in place. When all the coils are in place, and then now we can then remove it. So we created 2 prototypes of the machine. So we developed 2 prototypes of the machine. So the first prototype was a 3-pole pair, and this prototype was some sort of test, because when we were developing this prototype, we were still trying to understand how best you can, deal with the coils. So, and you see the final design was somehow neat. And when we understood this process very well, then now we went now to develop now a much more complex prototype, which is a 6-pole pair prototype. And for this 6-pole pair prototype too, the winding process was really challenging because all the wires are in space. So you have to always, like for this one is 10, like we do 10 turns. We use 40 strands of wire, and then we turn it around 10 times. So we have like 400 strands. So each face here has 400 strands of wire. And for this one, since we have two that comes in one whole shoe here, so you have like 800 strands of wire that you have to put in place. So it was quite challenging, but we used the experience that we had for the initial one, and then we could come out with something that looks much more beautiful. You can see it here. And for this one, you can see I tried to put colors, just like I explained initially, to show the differences of the face, so that you see this is actually a different face of wire. This is actually a different face of wire. And then for the rotor too, the rotor part of the 3-pole pair prototype was not too challenging to wire, but the rotor type of the 6-pole pair too was also very challenging because we had to deal with 800 strands of wire. So, but finally, we always use we first always try initial prototype, and then now we use the experience to develop a much more complex one. So finally, we have now the the rotor of the 6-pole pair were assembled and linked. And you can see now, to put it in perspective, you can see the two machines. So you have, this is the 6-pole pair type. It has a lot of wire actually. And this is the 4-pole, the 3-pole pair type. 3-pole pair type is neat and not so complex. But this is the final assembled prototypes with all their wires in place. Then now the next thing was to do actual measurement, to measure the inductance, because now we have the actual prototype, so we don't have to do anything analytically or through final element analysis. However, we can still we have to use final element analysis to determine the inductances, and then now we can compare with actual prototype. So but now we use the ZM2355 NFLROC meter. So this meter I first start by measuring a 33 centimeter 0.2 millimeter diameter of the wire. That is, I measured one strand of that wire that is 33 centimeter long, and I calculated the resistance, and then now I measured now the resistance of that same strand of wire with this LC arrometer, just to understand the differences that exist between the analytical and the measured type. So from this one, I can now understand the error rate, so that when I'm measuring now, I'm not okay. Analytically, I have this value, and when I measure one strand, I have this error. So if I'm to measure the actual machine, I should always take this error rate into consideration, and which is what I did here. And for this one, I measured the first for the stator windings of the 3-pole pair. I measured the phase A and phase B inductance, and for the 6-pole pair, I measured the phase A and phase B inductance. And then for the 6-pole pair now, I measure stator windings, it has phase A and phase B. And then the rotor type, the rotor side for the 6-pole pair to measure the phase A and phase B. So we measured all the inductances of the actual prototype that was made. And then now we did assembling, try now to put the coils, this stator holder, this stator coil holder, we put it in place inside the stator, and then now try to assemble it and try to see how if it assembles well without any sort of like any friction, because it should be very, very light, because the machine doesn't have any magnet. So we just want a machine that even the simplest power can produce that torque. So it was quite good. This was okay, and the final assembly is like this. But this one will make some. The final assembly when it is fully assembled, it looks like that. So now for the axial gap type, since we already did the analysis of axial gap type, I also decided to just build it at once. So we build the axial gap type, and it's also very, very somehow very, very difficult to wire it, because since the shape is different, and this is the first prototype of the axial gap type, so it was challenging to wire. Maybe I'm going to make a second prototype, and I think it's going to be easier, because I now understand the process that I can use to make it easier. But however, we have now the fully wired axial gap type. This is the stator of the axial gap type, and this is the rotor, and this is the entire machine. You need to have a stator and a stator back to hold it, and then the rotor, and then now these are like screws to screw it and put it in place. And for a tentative assembly, it's going to look like this. Yeah. And now the next thing is we need an electronic system to drive that machine to make it create that torque, because we're going to use the idea of, since we're using the resonance circuit, so we need some sort of frequency generator that generates frequency, and then we amplify the frequency that was generated, and then we transfer it, like we make it resonant and then transfer it. This is the basic idea of resonant magnetic coupling. So we try to couple through coils without wire, we couple through magnetic field. So this is the idea, and it means that we have to design an electronic system that is based on this, because this is how the machine works, the motor works. So the main idea is we are going to have we are going to use a frequency generator, we generate frequency low voltage, and then we use an amplifier. Then we amplify the frequency, we make it resonant, and then we pass it through one of the phase coils, and then it meets the other phase coil at the motor side, and you can create rotation. And we're going to add some sort of microcontroller that will control this frequency, and then that microcontroller you can still add, like, measure some sort of like current here. So but for this electronic circuit that this electronic system design, this is going to be the target design parameter. So we want a system that will have from between 50 to about 200 volts, and then we want the frequency to go from 10 to about 200 kilohertz, and we want the current to be from around 5 to 30 amperes. So the main idea of the design is that we want something that is easy and modular, so that you can easily add it. And then we're going to use a very simplified design. So we use design techniques that are well known, nothing new. And then we try to make some sort of flexibility so we can change the frequency. So we're going to use a microcontroller. So if we design one of it and make it modular, we can use two of them, because for running this machine, since we have two phase coils, we need two of this inverter. So we just focus on designing one, and then now we try to use two of the design to run the machine. That is the main idea. And for the microcontroller, it produces two waves that we are going to be, the waves are going to be, the two coil of voltage are going to be like 100 and it's going to be 90 degrees out of phase. And then we engage in the design. For the design, we use a full bridge topology, and this is the analysis of it. We use LT-SPICE to design the main circuit of the machine. We run a model of it in LT-SPICE. We focus on designing just the phase A side, because the phase B side is the same. So we did analysis many times, modified the design, and came out with a design that was better. Then went further to do more analysis, and we're going to see the current and the voltage is going to be something like this. Try to analyze the FFT spectrum of this. We still have to improve it, but so far we just use the design prototype is just based on this. Now the next is to design. We design now the main electronic circuit to create what we did by simulation, and this is the main design of the machine. So this is the main amplifier part, and this is the main microcontroller. And these are some parts to indicate how current flows inside. We have some gate drivers, and then we have some part where we have to connect the two boards as master and slave. And then we use this electronic circuit, we translated it to a PCB board. We drew the PCB in KiCad, and after drawing that, we made now the board itself. So the board looks like this. We'll use computer-aided tools to model how it's going to look in reality. So this is going to be the front side of the board when all the components are assembled, and then this is going to be the back side of the board. And the final board is going to look something like this. And if it is well assembled, the board should be like this. So, and then now we send this design, and this is the final board that was made based on our design. And we receive 5 of the boards. And this is the front side of the actual implemented board. This is the back side. And for the board, we have the main power MOSFET with the amplifier. We have the sections that we are going to connect to the main machine. We have some sections to measure. And then we have some resonance capacitor that we added for 200 kilohertz. And then the input voltage. But the idea, of course, like I indicated before, we need two of these. We need two of this driver to run the motor. So what we did is to assemble it, move away and how we can assemble assembly procedure to assemble two of the board. And if we assemble two of the boards for the multi-phase, for the two-phase, it's going to be something like this. And this is the final design that is implemented in our lab. The final assembly is something like this. And then we started doing pre-test to generate the frequency. We were able to generate the frequency and amplify it, but we are still running it, and one side of it is working, the other side is trying to troubleshoot. So I'll continue now with final discussions and conclusions and future work. So for the final discussion that I want to talk, further discussion is the final test bench. So we also develop a test bench of testing the machine. And just a small test bench that is about 60 centimeters in length, this test bench, and we can assemble the machine here. This is a 3-pole pair type that should be assembled and then put placed on the test bench. And this is the total machine. We have the 2 types. This is the Azada, and then this is the main electronic to drive the whole machine. And this is the total system in place. So now the next stage now is we are trying to see how we can test the machine. And this is the final machine, all parts together. And for future works, we also, alongside, we are also developing a PCB type. So for the PCB type, we have the idea of using the Asia gap type, and then for the Asia gap type, we have the coils placed like this. So what we want to do is I want to change these coils into PCB traces. And if we keep changing the PCB traces, it's going to look like this when we draw it like this, and then we can translate it like that. But since these traces are so tiny, so we are going to use 10 layers to reconstitute the density, the thickness of these wires. But the reality is, if we want to make the actual thickness of the wire, we are going to need about, I can try to estimate it's going to be more than 50 layers, because these traces, the wires that we can use, the wire of 0.1 or 0.2 millimeters too, then we will need about maybe 50 layers to reconstitute this same kind of thickness. But for this one, for just proof of concept, we did for 5 layers, and then this is the idea of how we are going to interconnect. This is going to be layer 1, let's say layer 1, layer 2, and then we're going to interconnect the layers of different pole pairs. So it's going to be interlayer. So let's say if we have a phase in this layer, the next layer is going to be phase B, and then only the 10th layer is going to be phase A again. So we are going to be some sort of like sandwiching interlayers, and the model is going to look something like this, and then the final design should be something like this, that will have 2 layers. We have a bearing, and then we have some sort of shaft that is going to be attached to the part of the rotor, and something like this. So this is for future work and further work, can be like perspective for other research avenues. So in conclusion, so to conclude this presentation, during our PhD journey, I've achieved the following. So we proposed the theory of this kind of machine, and then we tried to develop an analytical model of the inductance. We corrected many times, and then we used final element analysis to validate the model that was developed. We also developed a frequency model, and used this frequency model to explain the capacitance that we need. And we extended the study to include axial gap type, and then further developed the prototypes of 3 prototypes, 2 radial gap type and 1 axial flux type. And then we have implemented the hardware prototype of the driver. So what is left is just to conclude and run more experiments. And to finally, different part of this research has been published, have already been published. Some of them have been submitted, and then some other part of the research is still currently under preparation. So for the papers that we have published so far, we have published a list of papers, and a list of papers that we published during this research. And then we have, finally, we have some other papers that is still in preparation. And finally, I just want to use this opportunity to also thank Besong for all his guidance and assistance support, and making me a better researcher since I joined this camp. So thank you, Sensei. And thank you for your kind attention. If you have any questions, please don't hesitate to ask.
Dziękuję bardzo.